All right, so in the last video, we wrote a small assembly program that prints out Fibonacci numbers, and we introduced a small logic error on purpose so that we can take a look at that in this video. But theoretically, it was supposed to print out Fibonacci numbers until the number 317,811 right up here. And if you don't remember what that looks like, let me just pull up my build tools here. And we'll just go ahead and run it. And so you can see it goes to one number over our stated max, but it prints out Fibonacci numbers. So in this video, we're going to use x64 debug, and we're going to take a look and step through the program and take a look at the memory, the registers, and the CPU instructions. All right, so the first thing we're going to want to do is open our program. Fibonacci loop. And we are going to want to set a breakpoint where the meat and potatoes of our code starts. So I want to set a breakpoint. We could set one at ASM main, but we're going to set one at next fib number, because that's where most of the interesting things that happen in our program take place. So I'm going to go to symbols if you're following along at home. I'm going to click on Fibonacci loop.exe. I'm going to search for next fib number right here. And you can see the address that's at. And we'll go ahead and jump there. And so I want to set a breakpoint here so that every time we go through this loop, we get the opportunity to step through this step by step. Okay, and so I'm going to run the program to this point. And this is our RIP register, the instruction pointer, and this points to the next instruction that's going to be executed by our CPU. So let's take a quick moment and compare where we're at this very second with the program that we wrote. Okay. So we have our first int, second int, our new fib number, and our max int. The only thing that we expect to be in a register at this point is our maximum integer in R14. And we can see R14 does indeed contain the hexadecimal value for 317,811 right up here. Okay, so what next? When we start this, so we haven't executed this yet, but we expect to move whatever is in first int, so 1, into the EDX register up here. RDX, right? Now RDX already contains 1, but we can't count on that because we didn't move it there. The second thing that we want to look for is that whatever's in second int, right, is moved into ECX. Second int should contain 1. And then we will move whatever is in RDX into R15. We will then add RCX and RDX together. And then we will move RDX back into the first int memory location, and then R15 into the second integer memory location. So let's go ahead and step through that and see if that's what happens. So we're just going to take the next step. And we can see that RDX now contains 1. It already contained 1, but we had to make sure of that in our procedure. So we take our second step, and ECX should now contain 1. What does ECX contain now? F, right? So we will take the next step, and you can see that RCX now contains 1. Next, we're moving whatever's in RDX into R15. So we're moving 1 into R15, which currently contains all zeros. Now we're adding RCX and RDX. So RCX 1 and RDX 1. Now remember, when you do an add operand or operation, excuse me, whatever the sum is moves into RDX, which is why we have to copy the contents of RDX into R15 before we do this, because we'll destroy the previous sum. And so we'll go ahead and add that. So RDX will contain 2 after this step. Now, here you're going to see D-word pointer to first int, right? Well, what is that? That's a memory location, right? So how do we know what's in this memory location? Well, we can look at following this in dump, the memory dump. So 7FF777AC4000. So let's go ahead and follow that in dump. And you can see the memory location of first int. This is actually what's held in the computer memory. So we'll go ahead and step into our next instruction, so after this, we should move whatever is in EDX into here. Now EDX contains 2, so our next instruction should force this place in memory to contain 2. Next, we are moving the contents of R15 into second int, right? Well, let's go take a look at second int. We'll follow that in the dump. And that currently contains 1. We are moving R15, 1, into that location in memory. It already contained that, so it doesn't look like anything changed. Now we are loading whatever is in fibprint into RCX, right? And so we can see that's an AAEFBD. And so we can trace that, or if you actually want to look at the sections of the file, we'll take a look at our memory map. And you can see, because it expects to be in AAEFBD, we can see AAE would contain, it'd be between these two memory addresses, so it'd be in this dump somewhere. And AAEFBD, AAE, AAEFB, okay. So we can see that this memory address is actually what contains the string, right? So when we load the address of fibprint, we are not loading next number into RCX. RCX will not contain the string next number. What it will contain is the address of the string next number in memory. So the address of the next number is 7, this memory address ending in FBD. And so when we step through the next instruction, you can see that the address of the memory location is what's in the register. Now we want to call printf, and so this will print an output, and we do have an output box here, so I will go through this and then we will see our first output is 2, right? And now we want to compare R14 and R15. R14 and R15. And this will set flags. And if R15 is less than R14, we want to jump back to next fib number. If R15 is greater than or equal to our max number, we want to jump to our end routine. And actually, before we do anything else, let me set a breakpoint at our end routine. Oh, it was right there. Okay. Okay, so we are going to compare, and then because R15, of course, 1 is less than 300,000, we will jump back up here, and you can see our IP pointer moved right back. And so let's follow the progress in memory. Let's go. So we can see currently our first number is 2, and we'll run through this whole loop again. So you can see as we run through this loop, this is our first Fibonacci number, this is our second Fibonacci number, so this will become 8 and this will become 5. And then this will become 13 and this will become 8. And so this will keep happening until what we compare is greater than or equal to our max number. Now, just a quick point here. This says 0D, right? That's hexadecimal for 13. So that's why, again, it's important to know your data representation. But you can kind of start to see the problem as we go through this. R15 is compared instead of what our actual end Fibonacci number was. So if we keep going, you can see now that R15 and R14 are the same numbers. However, down here in memory, so you can see the R14 and R15 memory addresses, or what should have been contained in them because of first and second int. And then we can see what's actually contained in first int here, right? This is 07 D8 B5. And in hex, let me pull up a piece of paper here. That is 5 in our 1's place, 176 in our 16's place, 2048 in our 256 place, 53,248 in our 4096 place, and 458,752 in our 65,536 place, which altogether equals 514,229. That is greater than 317,811 we expect. The reason for that is that we stored, so up here, we move EDX into, we move first into EDX, second into EDX, add them, but here we've moved RDX into R15, and down here we're comparing R15 and R14. So let's fix that real fast. There's a couple ways we can do this. So first, let's take a look at this program. So when I first wrote out this program, before I decided to introduce a logic error, I added the fib number variable. Now, the fib number variable was going to contain the final Fibonacci number of each sequence, and then first int and second int were not going to be necessarily overwritten until the end of the next cycle. So what we were going to do is compare the fib number. However, we don't use this variable anymore. And so let's get rid of it. And before we compare, what we could do is move, right, so we have our first int so the EDX is moved into our first int, and then R15 is moved into our second int. So what we could do is move our first int into R15. So R15 first int. Now if we build this, our debugger has it open at the moment, so let's, okay. you can see that now we hit the proper number. We hit our max int. So let's open this back up. Let's make sure our breakpoints are set. Sometimes they carry over, sometimes they don't. Okay, we still have ours, so we'll go ahead and run the code to here, and we'll set one for the end routine as well. Okay, and let me open this in memory so that we can follow along. Right here. Oh, actually, you can see the output, excuse me. So we'll go ahead and run this. And you can see we're at 6,765. And now we are at our maximum, and so we're going to call our end routine, right? So what happens when we call our end routine? Well, let me do a window capture again. So we are jumping if greater than or equal to our end routine, and then we are adding 38 back onto the stack, so we're moving the RSP, the stack pointer, and then we're returning control to the C wrapper program. Now you can see here how this would mirror what our assembly code was. We have our label for end routine. We're adding back on to the stack pointer, and we're returning the control to our C program, right? So we're returning that to, after ask main, we're returning to here where it will print %s terminated. And then if there's any issues, we have this catch block. So we'll go ahead and run this one more step, which will complete it. And we're done. That's the inner workings of how our Fibonacci number printer worked and the way to fix the logic error that we introduced.